I think everybody's interested in volcanoes, at least I am. It's sort of a fun topic. Before we really get into it, there are three words, though, that I want to sort of define for you because they're sort of used by people and without really knowing what they mean, especially one: active, dormant, and extinct. Let's take active first. Active means that it's active. Now, the point being, however, that it doesn't necessarily have to be an eruption. Obviously, an erupting volcano is an active volcano. But to be active doesn't require active molten rock coming out. Any indication that the fire's lit down below, that's all you really need. So if you have, for example, whiffs of steam, for example, if you went to Mount St. Helens today, what you would see today is no evolution of lava anymore, but what you would see would be steam coming out of the crater. That's an indication of activity. Perhaps just the fact that the rocks within the crater are warmer than the rocks outside the crater. Maybe that's all you really need to have. So the point is, for active to be an active volcano simply has to indicate the fire's lit. It could come back at any moment. So that's active. Now, extinct means it's dead. The fire's out. The molten rock no longer exists down there. It's all solidified. It's not coming back anymore, so you can forget about it. That's extinct. The problem is this dormant stage. Now, dormant means different things, I think, to different people, but in talking to volcanologists and asking them what does dormant mean to you, I get the idea in general that what dormant means is you've got a volcano that perhaps doesn't show any sign of activity, that hasn't erupted in perhaps a very long time, and yet there's a gut feeling that the fire's not out, that this thing could come back again. And so they don't want to chalk it off the list yet. So that basically was what dormant's all about. Now, the real problem is that historically there have been lots of examples of extinct volcanoes that were really just asleep. Now, the best example I can think of, let's see, this would have started about maybe 100,000 years ago on the peninsula that we now call Italy. There was a volcano that was created, we call it Mount Somma. And Mount Somma, by all indications of the deposits around her, or what's left of her, indicated she had a very long and active career. And then she went into dormancy for a while. And then she had this monstrous eruption. This is estimated a few tens of thousands of years ago. And the cone itself, the mountain cone itself of Mount Somma, was almost completely destroyed. But out of it rose another volcano. And the volcano that rose out of the remains of old Mount Somma was what we call Mount Vesuvius. Again, Mount Vesuvius went into a series of eruptions and activity for quite some time, and then she went asleep. Now, the point is, when the Italians, as we know them today, and the Romans moved into the area, they had never known this mountain we call Mount Vesuvius now. They had never known it to have any indication of activity whatsoever. It had never erupted. There was no indication of any life down below. Matter of fact, they even farmed the slopes, and down inside they had vineyards and the whole bit. So they classified it as extinct. So to the Romans, this mountain was extinct. Well, that went on okay until about 150 BC, when it went into a state of eruption. All of a sudden, Mount Vesuvius said, I wasn't dead, I was just asleep. And so she came back to life in about 150 BC. And then that activity went on periodically over a period of time for about, what would it be, about 220 some years. And then on the 24th of August, in the year 79 AD, it really erupted and went into an eruption. We'll talk about various phases of eruption a little bit later. A gigantic eruption this was. And as a result, there were two little towns at the base of Mount Somma. Naples now, of course, did not exist at the time, but there were two little towns at the base of Mount Somma, one of which you may never have heard of, called Herculaneum. But the other one I'm sure you have is called Pompeii. Now, Herculaneum was destroyed apparently within a very short time, perhaps within a matter of hours, by mud flows. Now, these mud flows are referred to in volcano terms as lahars. So if you hear the word lahar, what that is, it's simply a mud flow associated with a volcanic eruption. Now, these things are very, very destructive. What happens during a volcanic eruption, if the peak is high enough, of course, it has snow and ice on it, which melts, and now you have generating lots and lots of water to mix with the very fine materials being erupted from the volcano, the dust and the ash, making a mud. And in addition to that, it's quite frequent that you have torrential rains because this reaction above the volcano disturbs the atmosphere, so torrential rains are very, very common. So to make a long story short, you have a lot of water, a lot of mud being created, and down the mountainside it goes and is a big destroyer. For example, in the case of Mount St. Helens that went up back, 20 years ago now, the big destroyer was a lahar mud flow that went down the Toutle River and took out people's homes and took out bridges, the whole bit. And that's where most of the destruction was affected. The trees that were all blown down, I think they harvested most of those, so I don't think that was really a loss. But anyway, these mud flows are very, very destructive. Well, anyway, Herculaneum was destroyed within a matter probably of hours and buried. Now, Pompeii took a little bit longer. Pompeii died over a few days. It was being pelted with molten rock that was falling out of the sky, and molten rock was coming down the streets. But anyway, eventually Pompeii was then finally covered too, and they lay buried like that for, let's see, it was in the 1700s, I guess, when they were first discovered. And since that time, of course, they've uncovered both of these little towns. And in fact, a lot of what we know about Roman history and about Roman life was gotten by the things that were preserved in these two towns. We see their buildings, we see their architecture, we see their art, tile floors and baths and things like that. You see the pictures of the molds of bodies. Well, some of those actually preservations were so good that apparently they actually had the hairstyles of some of the women preserved. So it was really pretty well preserved. So anyway, that would have been a good example of a extinct volcano that was really dormant. So anyway, there's the description. Now, it's been known for a long time where the volcanoes of the world are, and for hundreds and hundreds of years, the main volcanoes of the world have been known, and most of them, it turned out, were around the Pacific Ocean. As a matter of fact, they refer to that ring around the Pacific Ocean as the Ring of Fire. That's even today, that's where the great percentage of active volcanoes are. Well, you see, they knew about that long before, let's say, the days of plate tectonics. They also knew, for example, that there was a chain of volcanoes that went down through the Mediterranean, Mount Vesuvius, Mount Etna being the two most well-known. And there was also a chain, of course, Indonesia. So those mountains have been known for a long time. But it took plate tectonics, first of all, to understand why they were there. See, we never understood why they were where they are. But it took plate tectonics. Now we do indeed understand why. So if we look to see where the volcanoes are today, most of the volcanoes that you see now are located obviously in the convergent margins. We're talking zones of subduction. Now, the thing about these volcanoes, these, for a reason we're going to talk about shortly, these are all potential killer volcanoes. When these things erupt, they have the potential to kill people. So they're always violent eruptions along the convergent boundaries or the so-called zones of subduction. But as a result of plate tectonics, we found out there was another place where volcanoes were erupting too. They were on the ocean bottom. We're talking, of course, about the oceanic ridges. And, of course, the other places, the rift zone, the rift valleys too. But the oceanic ridges, we never knew about those because they essentially were submarine. Except, of course, for a few places where the heads poke above water. And, of course, the most classic example would be Iceland. As a matter of fact, when it comes down to volume on volume of molten rock extruded onto the surface of the Earth, there has to be more extruded along the divergent margins, the oceanic ridges, than along the convergent margins. Figure it now. You got the whole oceanic crust. That's covering 70% of the Earth's surface right there. So we know the divergent margins. So that was plate tectonics taught us about that. And we understand that now. Now, here's the thing we're going to have to explain, though. All the eruptions along the divergent margins, none of those are killers. Now, no one's ever been down on a ridge to see it. Well, yes, we have, really, because Iceland is part of the North Atlantic Ridge. We see the eruptions on Iceland, and none of them are killer volcanoes. So one of the questions we're going to have to answer shortly is, why is it that the volcanoes associated with the convergent margins are always explosive and potential killers, and those associated with the divergent margins, the oceanic ridges, are not? Well, we get around to that. Well, anyway, there's one other site now of volcanic activity that we haven't talked about yet, and I've saved it till now. They're called hotspots. Now, these are very mysterious. I say mysterious because we really don't understand them. First of all, they have nothing to do whatsoever with plate tectonics, so we can call on plate tectonics to help us out. These have nothing to do with plate tectonics. What they are? Well, what they are, coming up from deep within the Earth's mantle, some people say possibly as far down as the core, you have these fingers of heat. Now, just a finger of heat now, not where it's coming up under a ridge line, but a finger of heat. They call it a mantle plume. The mantle plume comes up through the mantle, comes up through the asthenosphere, right to the top of the asthenosphere, and right there, molten rock forms. It's always basaltic magma, always basaltic magma. That's the hot spot. So the hot spot we're referring to is this concentration of basaltic magma at the top of these mantle plumes. Now, what we know about them? Well, there are about 100 of them today, active ones that we know of. The interesting thing about these things is most of them are under the ocean basins. Why? I'm not really sure. There are a few under continental crust, but most of them are under the ocean basin, so we don't really know the reason for that. Here's the other interesting thing about them. Once they form, wherever they form, they don't move. They stay where they are until they finally die. Now, that's an interesting thing, too, because you picture now this mantle plume sitting there after having come all the way up through the asthenosphere. Above it, of course, you got, let's say, an oceanic plate moving, has no effect upon the location of that hotspot. It stays right there. And here's something else that, personally, I had a very difficult time picturing how this works. Here you have this mantle plume now crossing the asthenosphere. Within the asthenosphere, you have these moving masses of rock driven by those convection cells, and you have this mantle plume that comes all the way across one of those things without any effect of it. I don't quite understand that one. I find that very difficult to picture in my own mind. I think the real answer to all of this is what really goes on down below the surface, down within that asthenosphere and lower, we really don't quite understand. There are lots of things going on we probably haven't even seen yet in any way. So anyway, that's what a hot spot is. Now, in the case of the hot spot, what happens is the mantle, the magma breaks through to the surface and starts to build volcanoes, and I'll show you what kind of volcanoes it builds. So these are sources now of volcanic activity that will hold what kind it is until a little bit later. But what I want to talk about now is the intensities. Why are the volcanoes associated with zones of subduction potential killers, and why are those associated with either the hot spots or, in the case of the oceanic ridges, why are they not? They are never killer volcanoes. They are never explosive eruptions. And why not? Well, let's talk about what makes an explosion. Now, I don't really care what kind of explosion it is, whether it's a volcano erupting, whether it's a firecracker going off, whether it's a stick of dynamite exploding. What an explosion is simply the rapid release and expansion of gas. That's it. It's just a rapid generation of gas. That's what an explosion is all about. So the way it works is very simple. Whether you have an explosive eruption or not is simply going to be a function of how much gas is involved in the magma at the point at which it reaches the surface. If there's a lot, you can expect a big eruption, a violent one, an explosive one. But if there isn't very much, then you're going to expect a very low intensity eruption. Well, the real question, of course, is what really controls that? So here's what I want you to picture. What I want you to picture are three magma chambers below the surface: basaltic magma, andesitic magma, and a granitic magma, side by side. Now, remember now the big difference between them. Obviously, there's a big difference in composition, but again, thinking back to our discussion of viscosity. The big difference in viscosity has to do with silica content. The silica content of the basaltic magma, about 45%. A very low viscosity. And remember, the sort of the little model I set out to compare that against would be like olive oil. And then the andesitic magma, about 55% silica, a little bit thicker, a little stickier, and the model there was going to be pancake syrup. So it gives you some idea of the comparison between basaltic now and the andesitic. The granitic over here now is between 75 and 80% silica, very thick, very sticky, and this one in comparison would have been molasses that you kept in the fridge for about a day. So you get a feeling for the difference in viscosity. Now, so what? Well, now let's just picture in general what happens whenever one of these magma chambers is open to the surface. All of a sudden, pressure is relieved. Now, I once read, I don't remember who did this, but he likened an eruption to opening a bottle of champagne. And, you know, he pictured this thing, you know, you pop that top off and there's a big eruption of all the champagne come out. Right off the bat, if that's the way you open your bottle of champagne, you're not doing it right. Now, since this is supposed to be an education course, I thought maybe I'd just take a minute to tell you the proper way to open a bottle of champagne. The proper way to open a bottle of champagne, of course, is not to have that big pop and lose all that champagne. The way you do it is you basically take off the foil. You got a cork that's caged in. The reason why is because the pressure inside a champagne bottle is very, very high. Remember, they ferment it right in the bottle. And that's the reason why it's so thick. So what you do, you turn that little tab 7 turns. Not 6, not 8, 7, and it opens. When that thing pops up, you grab that cork, but you never let the cork go. What you do is you rotate the bottle. And as you rotate the bottle very slowly, the cork, if it just pops like that, you've done it properly. You haven't lost any champagne, and you've opened the bottle properly. Now, what happens down inside the champagne is the same thing that happens inside this magma chamber. What happens is the gases in solution, in this case of the champagne is carbon dioxide. Now in these magmas, what kind of gases are in there? Well, we're going to talk about the gases evolved during an eruption, and there's no reason to believe that all 3 of these don't have the same amount of gas, or maybe even kinds of gas. But to come out, first of all, just picture this now, for the gas to come out of solution, it has to make a bubble. Now to do that, some of that liquid, whatever it is, has to flow out of the way to allow the bubble to form. And then the bubble has to get big enough to have the buoyancy to rise to the surface. So in order for it to do that, more of the liquid has to flow out of the way. And eventually the bubble gets to the point where it's big enough to have the buoyancy to rise to the top of the liquid. And to do that, the liquid has to flow out of the way and let it go by until it finally gets to the surface and then is vented to the atmosphere. Flowing out of the way, you see, that has to do with viscosity. All right, so let's picture now the basaltic magma. We're talking an eruption now associated with any of the divergent margins, or now, as we'll see, of those hot spots. The vent opens to the surface. The magma starts on its way up through the crack. Now, this is basaltic. Because of low viscosity, the bubbles start to come out, rise through the magma, venting at the surface, even when the magma is on its way up. Okay, so by the time the magma gets to the surface and is ready to break into the atmosphere, most of the gas now is gone. And what happens is there may be enough gas to blow the magma up in the air, maybe 1,000 feet, maybe 2 at the most, and form a fire fountain, but there's no explosion. You don't have to worry about it. There's not enough gas to make a big explosion. And then it all settles down, and then the magma simply pours out and fills maybe a little lava lake and flows downhill to the ocean or wherever it's going to go. So that would be a typical basaltic eruption. No explosion. Now let's take the andesitic. Now we're talking now about the magmas that are going to come to the surface at your arc volcanoes. Same thing, the only difference is as it makes its way up through that little crack to the surface, the venting of the gas is going to be considerably slowed down because of the viscosity of the magma. And so by the time it gets to the surface, you're still going to have lots of gas left. Certainly there's going to be enough for an explosive eruption. Always explosive. Now, how explosive it's going to be is simply a function of how much gas is there. The more gas you have, the bigger the explosion. That's the difference between, for example, the eruption of Mount St. Helens, which wasn't a really big one, and Pinatubo, that destroyed Clark Air Force Base in the Philippine Islands. It was simply the amount of gas that's involved. So anyway, all those andesitic eruptions are always explosive and potential killers. Now, over here with the granitic. Well, the thing about the granitic is it probably isn't going to get to the surface anyway because it's so thick and sticky it just can't hardly get there. But what if it did? What if this granitic magma loaded with gas makes it to the surface? It's too thick to vent any of it on the way up. So when it gets to the surface, whatever gas it had is still there and it's got to come out. And when it comes out, it's going to be an eruption the likes of which have never been seen on the face of this earth in all of historic time. But before we're done with this course, I'm going to tell you a place where one of those kind of eruptions has happened. Some of you may want to visit it. Okay, so much for now. Now you see why the eruptions are of different intensity. It's simply a function of gas. Well, let's talk about some of the materials blown out. The materials, of course, fall in gas, liquid and solid. Let's take the gases first. The most voluminous gas evolved during any volcanic eruption is water vapor. Here's a question. Where did the water come from in the first place? How did the water get down there into that magma? Well, we think the water that we're talking about here erupting in a volcanic eruption was originally brought to the Earth during the impact of comets back in the primeval days. So anyway, that's the biggest gas coming out. Most of the billowing cloud you see, other than ash and stuff, a lot of that is just steam. Condensed water vapor is steam. But there's some other ones that are important. Carbon dioxide, for example. Carbon dioxide, which is our workhorse greenhouse gas, here's one of the sources of it. One of the sources is volcanic eruptions. The other source, I might add, is the decay of once living tissue. So those are the two sources to put carbon dioxide into our atmosphere. So that would be one of the gases. And then, if you've ever been to an active area, it really doesn't smell too good. Because one of the gases is very common is H2S, the smell of rotten eggs. That's one of them. And then you have all these XOX gases. SOX, SOXes. These would be the smell of fire and brimstone. And then you have acids. All kinds of acids are in vapor form. And that's the reason why you don't usually see much in the way of plant life around an active site, because it just isn't very hospitable. So those are the gases. Lots and lots of gas. Then we have the solid stuff. We call this just in general pyroclastic. Clastic in geology means you're talking about bits and pieces of rock moved from one place to another. Pyro means born of fire. So it's a very descriptive term. Bits and pieces of rock, born of fire, carried from one place to another. So pyroclastic stuff. The names we give pretty much are based upon size. The big guys are called either blocks, which are simply the remains of rocks that were there and blasted apart during the eruption, or bombs. The bombs are liquid rock that were thrown through the air large enough to take on some kind of an aerodynamic shape before they finally fell solid. And so those would be the bombs. They're usually in size greater than a baseball. And then under that, you have a large volume of things called cinders. Cinders are usually range from maybe baseball size down to maybe pea size and things like that. And in my experience in looking at volcanic areas, it seems to me there's more of that stuff than anything else, but I'm not really sure that's true. But then what I want to talk about, though, is the really fine stuff, the ash and the dust, especially the dust. Because if it's blown into the atmosphere, let's say to elevations of 30,000 feet, 40,000 feet, this is picked up by the prevailing winds and can be carried around the world and affect world climate. Interesting, the first person to ever predict that or make that statement that one volcanic eruption can affect world climate was Benjamin Franklin. He was quite a scientist. But anyway, case in point, I think it was in 1815, there was an eruption of a volcano by the name of Tambora, down in the Indonesian archipelago. This thing was so intense, there was so much ash and dust thrown into the upper atmosphere, it dropped the atmospheric temperature in the northern hemisphere for years. The year after, 1816, was called the year without a summer. They just didn't have one. Snow fell in New England and New York State on the 4th of July. Growing seasons were foreshortened because of freezing of crops. There were places where there was no growing season, no food was being produced. People were starving to death around the world and dying of course, disease brought on by starvation because of this one eruption now, one eruption. How many died? Nobody really knows. These were people who died because of an event at a place they didn't even know about. Question, could that happen again? Sure. But note what would happen if there was more than one. It could be very, very bad. So anyway, that's just a little thing to think about. All right, so anyway, the lavas now, the liquid stuff. Of course, we call it lava. When it comes up, the molten stuff is called lava. When it finally solidifies, it's called lava. Now, the names that you see applied to the solid lava, well, the original names were just sort of generic names, but most of them now are the Hawaiian names. For example, if you ever go to the island of Hawaii, one of the ones you'll see is the lava that spews out, ends up with a very smooth surface. Almost shiny smooth. Matter of fact, somebody thought it looked like plaited ropes at one time, so they called it ropey lava. Well, that was the old term. Now the volcanologists worldwide, they don't use rope anymore. They call it by the Hawaii name Pohoihoi. That even sounds smooth, Pohoihoi. And so that would be one variety. Now picture this basaltic lava coming out, and these names only apply to the basaltic lavas. Let's say the stuff is spewing out and it's moving along and it's cooling down and it's starting to get a little thicker because that's what happens when molten things start to cool off. And now it starts to sort of pile up and it's moving along very slowly. And the surface freezes over, but the inside is still molten and still moving. So the surface freezes over and breaks up and mixes in, and it keeps doing that until finally it's all said and done. You've got this lava that's finally solidified. It's just sharp and angular pieces. It looks like cinder blocks have been busted up and stuck back together again. But the old term was blocky. Well, I guess that's a pretty good term because that's what it does look like, blocky. But the Hawaiians have another term for it. They call it a'a. A'a lava is this very blocky lava that forms as a result of solidification of this slow-moving basaltic stuff. Then there's one other one, just called pillow lava. And the significance of pillow lava is this is lava that forms underwater. Now, picture now the oceanic ridge. Here you have all of this molten rock coming up along the oceanic ridge, erupting along the summit of the oceanic ridge, and solidifying underwater. So we're generating now lots and lots of pillow lavas. Now, if anywhere to ask you, what would be the most widespread single rock type on Earth's surface? Right off the bat, you can answer, well, the most widespread has to be whatever is on the bottom of the oceans because that covers 70% of the Earth's surface. And then if you think about that, what kind of rock is that? Well, it's basaltic rock. And what kind of basaltic rock? It's pillow lava because you see it formed at the ocean's crust underwater. So that's basically what makes up all of the ocean bottom. The so-called oceanic crust is essentially basaltic pillow lavas. But you don't have to actually freeze underwater to do that. For example, if you went to the big island of Hawaii today and you took a little trip down to the southern coast of Hawaii, what you would see would be this river of basaltic lava flowing down the hill and sort of freezing in various places on land, extending the land. But a lot of it just finally makes it right to the very edge of the ocean and plunges over the cliff into the ocean. As you might suspect, it's a very spectacular scene here with all the steam and stuff as it plunges down into the water. But they have gone underwater now with cameras, and what they see is that as that stuff plunges into the water, it sort of breaks off into blobs that falls to the bottom, and the blobs sort of pile up and solidify, but they're all sort of locked together like pillows. And that's why they call it pillow lava, because that's what it looks like. You took a bunch of pillows. And you know, I always thought it was sort of like the test for cooked icing. You know, if you ever to test cooked icing, or whether it's cooked well enough, you pour a little bit into water and it breaks into those little blobs and falls to the bottom. And if they sort of sit there momentarily before they flow together, then it's properly cooked. So I always sort of looked like the pillow lava was sort of Mom Nature's test for cooked lava? Well, whatever. So anyway, those are the different kind of lavas. So now to understand where the lavas, where the volcanoes are, you understand that. You understand why some volcanoes erupt violently and others do not. And you understand why the lavas look different. So the next time you go to Hawaii, you'll be able to understand everything that you see. Well, the next thing we want to talk about, continuing our discussion of volcanoes, we really want to talk a little bit more about the eruptive styles of some of these volcanoes. So that will be next.